1. Introduction. Why we are fascinated by the cosmos. Look up at the night sky. Out there, among the darkness, tiny sparks of light shimmer, distant, cold, yet somehow alive. Each one of those dots isn't just light. It's a world, a massive sphere of energy burning for billions of years. And somewhere, floating in that endless ocean, is us, a small blue planet, a tiny part of an enormous mechanism we call the cosmic system. Humanity has always looked to the heavens with a single question in mind. Where did we come from, and where is it all going? Long before telescopes, our ancestors drew constellations, tracked time by the movement of the stars, and imagined gods among them. Today, we don't need myths. We have knowledge. We can read the story written in the fabric of space itself. In this lecture, we'll travel from the very beginning, from the moment when there was no time, no matter, no space. We'll see how chaos turned into order, how the first stars ignited, and how entire galaxies, including our own solar system, were born. It's the story of how everything came to be, from nothing. 2. The beginning of everything, the Big Bang. Almost every scientist today agrees. Our universe began about 13.8 billion years ago with a single, extraordinary event, the Big Bang. But don't picture it as an explosion like a bomb going off in space, because space itself didn't exist yet. The Big Bang wasn't an explosion in space, it was an explosion of space. Time, energy, and matter all came into existence at that moment. In the very first instant, the universe was unimaginably hot and dense, far beyond what we can reproduce in any lab. Everything we know, every atom, planet, star, and even life itself was compressed into something smaller than an atom. Then, within fractions of a second, the universe began to expand. As it stretched, it cooled, and pure energy began turning into the first fundamental particles, quarks, electrons, and neutrinos. Quarks soon grouped together to form protons and neutrons, the building blocks of atomic nuclei. Just a few minutes later, the first simple atomic nuclei were born, mainly hydrogen, helium, and traces of lithium. This stage is known as primordial nucleosynthesis, the first chemical event in history. At this point, the universe was still shrouded in a thick, glowing fog of plasma. Light couldn't travel freely. It was constantly scattered by charged particles. For hundreds of thousands of years, the cosmos remained a blinding, opaque soup of energy and matter. Then, about 380,000 years later, something miraculous happened. The universe cooled enough for electrons to combine with nuclei, forming the first neutral atoms. The fog lifted. Light was free to travel. And that light is still around today. We can detect it as the cosmic microwave background, a faint glow that fills all of space, the afterglow of the Big Bang itself. 3. The formation of the first particles and stars. Once the universe became transparent, it continued to expand and cool. But it wasn't perfectly smooth. Tiny irregularities, areas where matter was just little denser than average, acted like seeds. Under the pull of gravity, those regions began to attract more and more matter, forming massive clouds of gas made mostly of hydrogen and helium. As these clouds grew denser, the pressure and temperature in their centers climbed. Eventually, the heat became so intense that nuclear fusion ignited. Atoms of hydrogen fused into helium, releasing tremendous energy. And just like that, the first stars were born. These early stars were enormous, tens or even hundreds of times more massive than our sun. They burned furiously, living short but spectacular lives. When they ran out of fuel, they exploded as supernovae, scattering heavier elements like carbon, oxygen, and iron across space. Those elements would later become the material for planets and for life. So when we say we are made of stardust, it's not poetry. It's literal truth. Every atom in your body was forged in the heart of a star that died long ago. From this grand cycle of birth and destruction, structure began to emerge. Stars gathered into galaxies, immense cities of billions of suns bound together by gravity. The universe, once a glowing fog, had transformed into a vast and intricate cosmic web. 4. Galaxies, the cities of the cosmos. After the first stars were born, the universe didn't stay empty for long. Gravity, that silent architect of everything, began pulling stars together into enormous structures. These became the galaxies. Immense collections of stars, gas, dust, and dark matter, all bound together by their mutual attraction. You can think of a galaxy as a city of stars. Some are small towns with a few million suns. Others, like our Milky Way, are vast metropolises containing hundreds of billions of them. Between these galaxies lies mostly empty space, a dark, cold ocean of nothingness stretching for unimaginable distances. Galaxies come in many shapes. Spiral galaxies like our Milky Way with elegant arms winding out from a bright central bulge. Elliptical galaxies, more like giant glowing spheres made mostly of older stars. And irregular galaxies, chaotic clouds of stars often twisted by collisions or gravitational encounters. And yes, galaxies collide. It sounds violent, but because stars are so far apart, they rarely crash into each other. Instead, their mutual gravity reshapes their forms, stretching them like cosmic taffy. These interactions trigger bursts of star formation, lighting up the universe with newborn suns. Over billions of years, galaxies formed gigantic clusters and filaments, weaving what we now call the cosmic web, a vast three-dimensional network connecting everything that exists. When we look deep into the night sky with powerful telescopes, we're not just seeing stars. We're seeing the grand architecture of the universe itself. And somewhere inside one of those countless spirals, in a quiet arm of a medium-sized galaxy, a small cloud of gas began to collapse. That cloud would one day become our solar system. 5. The birth of the solar system, our cosmic home. Roughly 4.6 billion years ago, in a corner of the Milky Way, a massive cloud of gas and dust, leftovers from earlier generations of stars, began to collapse under its own gravity. No one knows exactly what triggered it. Perhaps a nearby supernova explosion sent a shock wave that disturbed the cloud, forcing it to clump together. Whatever the cause, the result was the birth of our solar system. As the cloud collapsed, it began to spin, and just like a figure skater pulling in their arms, it spun faster and faster. Most of the mass gathered in the center, forming a hot, dense ball that would ignite as the sun. The rest flattened into a vast rotating disk of gas and dust, the protoplanetary disk where planets, moons, and asteroids would eventually form. Within this disk, tiny grains of dust stuck together, forming pebbles, rocks, and finally, massive planetesimals, the building blocks of planets. Collisions were frequent, sometimes catastrophic, but over millions of years, a kind of order emerged. The inner part of the disk, where it was hotter, produced small rocky worlds, Mercury, Venus, Earth, and Mars. Further out, where it was cooler and ices could exist, gas and ice giants formed: Jupiter, Saturn, Uranus, and Neptune. Our young solar system was a chaotic, violent place. Asteroids slammed into forming planets, comets rained from the outer reaches, and entire worlds were reshaped by massive impacts. In fact, Earth itself likely experienced a colossal collision early in its life, one that created our moon. After about 100 million years of turbulence, the system stabilized. The sun settled into a steady rhythm of fusion, and the planets took their orbits. A delicate balance was achieved, the balance that still holds today, billions of years later. 6. The sun, source of life. At the heart of it all shines the sun, a massive sphere of glowing plasma, containing 99.8% of the mass of the entire solar system. It's not just a source of light, it's the engine that makes everything possible. Inside the sun's core, hydrogen atoms fuse into helium through a process called nuclear fusion. In that process, a tiny fraction of mass turns into enormous amounts of energy, following Einstein's famous equation, E equals mc squared. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing enough energy to sustain life on Earth for eons. This energy radiates outward, first as gamma rays, then as visible light, infrared heat, and ultraviolet radiation. After traveling through space for about 8 minutes, it reaches Earth, warming our oceans, driving our weather, and powering the entire chain of life. But the sun isn't just a peaceful giver. It's also a dynamic, sometimes violent star. It erupts with solar flares and coronal mass ejections, massive blasts of charged particles that can affect satellites, power grids, and even cause beautiful auroras in our sky. Despite all its power, the sun is just one of roughly 200 billion stars in our galaxy. And yet for us it's unique, because without it, we wouldn't exist. Over the next billions of years, the sun will continue to burn steadily. Eventually, when it runs out of hydrogen, it will expand into a red giant, engulfing Mercury and Venus, and possibly Earth. Then it will shed its outer layers, leaving behind a dense core, a white dwarf, the final heartbeat of a once mighty star. But that's billions of years away. For now, the sun shines calmly, a reminder that even in the vast cold of space, warmth and light can endure.